So example 12 is saying to approximate the sum of the convergence series by using 6 terms, include an estimate of your maximum error. So what we're doing is the integral test, and the integral test has, again, this idea of the error bound. We can't find the actual sum, but we can find an upper bound or a limit to what the error is. And for the integral test, if you approximate the sum using, let's say, 5 terms, then you know that that sum is going to be within the integral from 5 to infinity of your rule of sequence of the actual sum, okay? You don't know what the actual error is. If you did, you would know the actual sum, but you can get an error bound, an upper limit to the error, okay? But remember, in order to use the integral test, a couple things need to be in place. First of all, most importantly, you need to be able to find the antiderivative of your rule of sequence. And then if that's the case, dogs have to cuss in prison, right? So the function has to be decreasing, continuous, and positive. All right, so they tell us that this one is a convergent series. We would probably intuitively say that it was anyway because we saw 1 over n squared earlier, went to 0 fast enough to have the sum converge, whereas 1 over n did not. So 1 over n to the 4th, which goes to the x-axis faster, should also converge. And that's going to be a convergent p-series, but they actually tell us, okay? So it says to use 6 terms. So here we go. We're going to say s sub 6 equals, and we'll use the calculator. Instead of listing it out, we'll just go straight to the calculator, which remember is alpha window. That accesses your math commands, and then it's number 2. By the way, if you hit the alpha and then you hit those and you're not sure, just kind of scroll left and right. You can get to the one you want, number 2. And you know what I'm going to do? I'm going to do kind of what Colin mentioned. We could be in any mode from the home screen. It doesn't really matter. Whatever mode we're in, though, is going to determine whether when we hit X, if it comes up as X, T, theta, or N. The only advantage to being in a particular mode, remember, is if you want to recall an equation from the home screen by hitting alpha trace, okay? So that would be the only benefit to being in a particular mode. But Collins mentioned yesterday that, and kind of made a good point, that if we want to see ends, we could go to sequential mode, and then from the home screen, it'll just look better. It'll feel nicer, maybe. And so who doesn't want to feel nice, right? Oops. So let's do it that way. So again, now I'm in sequential mode. When I hit the X button now, an N shows up, and we go from N equals 1 to infinity. So it says to use 6 terms for the partial sum, so I'll do that. And then 1 over n to the 4th. I'll just make it look kind of the same way. 1 over n to the 4th. So yeah, that was a good idea, Colin. I kind of like it. It doesn't take too much time to switch it over. If you were in parametric mode and that was T, that's fine. Home screen doesn't really care. There we go, and we'll write that down on our paper. S subscript 6 is 1.081, and I'm going to store that as A. So stow alpha A, enter. And on my paper then, iPad, I'm going to put equals A. Now, because I know the terms are positive and decreasing, I know that that's a good lower bound for the sum. The sum's not going to be any smaller than that. It's going to be bigger than that for sure because we keep adding terms. But I can figure out an error by using the integral remainder test. So here we go. The actual error, let me go ahead and write that. The actual error is going to be we'll call it R sub 6. We call it the remainder as well. It's another way to say it. What's left over from our approximation to the actual. So we use R for that, subscript 6. It's equal to the absolute value of the true sum S, which we don't know, minus S sub 6, which we just found. All right, and that's a pretty common thing, right? Actual minus, or theoretical minus observed is another way, like in the science class. And then we take the absolute value because we don't really care about the sign. We don't know what it is, but we do know that it's less than or equal to. Okay, here's where the error bound is. It's less than or equal to the integral from 6 to infinity of 1 over x to the 4th dx. So I took my rule of sequence, and I changed it as a function of x. And because I took the first 6 terms in my partial sum, that's my lower bound now for the integration. All right, so let's go ahead, bless you, and compute that. And we'll do it if like it's a free response, because if this were a free response, you might have to show this work. So this would be the, let's integrate it first. we have to be careful with the infinity. So that equals this. That's x to the negative fourth dx. And so if we integrate, we get, you add 1, you get negative 3, so you get negative a third. And here, when you integrate, that's where you want to change it to b. The limit as b goes to infinity. So it's a little bit more writing, but hopefully you get used to it. You get b to the negative third minus 6 to the negative third. And now you can evaluate it. What happens to b to the negative third as b goes to infinity? It goes to 0, yeah, because it's 1 over b cubed. So if that goes to 0, we're left with negative 1/3 and then minus 1 over 6 to the third. Okay, so again, it's a calculator question probably, so I'm going to go ahead and type that into my calculator now. And I'm going to go ahead and do this. Well, let me keep my equals going straight down. Oh, I didn't really have to because I just called that a 0. Oh, so I need to multiply them. You're right. I do need. I'm being very careless here. That is multiplication. You just saved us, Colin. Man, good idea. Put it in sequential mode, and then caught a careless mistake. That's why parentheses again should be your best friends. I needed them there and I didn't have them. And so it's better to have them and not need them than to need them and not have them. Like $1 million, right? All right. I don't need $1 million, but it's nice to have it, right? So let's go ahead and type that in. Negative 1/3. And Colin, you're getting a lot of credit now on the video, which is actually cool, right? It's kind of like being retweeted. And then I'll divide by negative 6 cubed. That should give me the same answer, right? Yeah. Syntax. Oh, thank you. Colin, you should have caught that before I hit enter. Times divided by. Times divided by. They didn't like that. So how about negative 1 divided by 3 divided by negative 6 cubed? That should work better. So that's a very small number. So I'll store that as alpha b. So this is cool. That number is my error bound. We call that the error bound. Okay. I know then that my actual sum is within that distance from the actual sum. That's pretty cool. So let me write that to, and we probably want to go more than 3 decimals for something like this. This is where like scientific notation comes into play. 0.001543, and again, I'm going to store that as b. I already did. So here we go. We now know this. We know that the actual sum is going to live within the following: s sub 6 as the lower bound, and s sub 6 plus the integral from 6 to infinity of 1 over x to the 4th dx. And so we can actually then come up with that interval, and I'll just recall it over here. S of 6 I stored as alpha a, which is 1.081. And then for the upper bound, I'll just take that and I will add to it that small number which I stored as alpha b. 1.0. All right, I'm going to write down more decimals here. This is because we've got a pretty accurate sum. 1.081, 1, 2, 3, 5, 3, 4. That's the partial sum. And then when I add the small error, I get 1.08266067744. And I wrote that down. So that's pretty good. We know the actual sum is somewhere between those two numbers. So it looks like at least the 2 decimals here, we know the sum's going to be 1.08. Now we do again have the luxury with these computing devices we call calculators to get an answer that is pretty much the correct answer to, for sure, at least 3 decimal places. Let's change that to, I don't know, I'm just kind of fond of what we've been doing, 20,000, right? So this will take a while. So as this is computing, just a reminder that if you need to review your identities, there's a Quizlet app that Mrs. Lincoln made. Right? Y'all can still use it, even though y'all are calculus students. It has the power reducing identities on there. One act play, we already mentioned that, right? The radium story about the dial painters. They always licked the end of their paintbrush because they had to hand paint radio or fluorescent paint onto hand dials so that they would luminesce in the dark. and they got radium poisoning. Okay, there it is, 1.082. So I'll come over here somewhere and I'll say the sum is approximately 1.082. 3. I'll put down another decimal. And if you then write that down and compare it, come on, is that number in our interval? 1.08123? Yeah. It's greater than 1.0811 and less than 0.826. Okay? So there you go. So pretty good stuff, right? And this is pretty remarkable stuff, finding the sum living within a certain small interval. Okay, and so with calculators, it almost becomes kind of a defunct practice, but the idea behind it is still pretty neat. The trade-off then before a calculator is if you wanted to narrow the sum down to a smaller interval, you'd have to do more calculations. You'd have to go out to a 7th term sum or an 8th term sum, which again is just tedious. And then your error is smaller as well. So you can kind of home in on the actual number. So the integral test, or the integral error, as I repeated yesterday, is not on the AP exam. But there are 2 other error bounds that are on the AP exam that work pretty much the exact same way. One of them is going to be the alternating series error, which we'll get to. And then the big one is that the last one at the end of the year, the very last section of the year, is called Lagrange error bound, or Taylor polynomial error. And it's exactly the same idea. And for some reason, Lagrange error bound is the one subject that most BC students struggle with. I don't know if it's because the last topic of the year and they're not really focused or what, but it's just this idea. That's all it is, okay? Any questions on that idea, error bound, finding intervals where sums can live? Now, if you ask me why this works, that's an entirely different question, okay? Someone came up with this idea. They proved it mathematically. And we've verified it now twice that the sum actually does live there. Okay, so we've got the nth term test. Yes? Yeah, the question was why do we use brackets instead of parentheses here? Yeah, there's no harm in using brackets, right? Because we're just saying that the sum actually lives in there. We know it's not going to be the left endpoint. We know for sure it's not going to be the left endpoint. So if we put parentheses there, that's going to be a safe bet, right? This is the maximum error bound added to the sum. So there is a chance, according to the theorem, that it could actually be that number. There's a chance, okay? It's the maximum error. And if the error was at a max, then that could be the sum. So we would want to keep the bracket around there. So if you wanted to make the interval smaller, like in theory, if you wanted to make the interval as small as possible, you could take away the left endpoint. But taking away the right endpoint would not be, I mean, it's probably not going to be the right endpoint, but we never know. The theorem says that that is the maximum error, and the error could be at a max. So it's one of those things where we say like 5 is less than 6, right? Is that a true statement? But is it also true to say 5 is less than or equal to 6? Yes, right? Have y'all ever eaten ice cream or done crack cocaine? Yeah, the answer is yes, right? Absolutely. So it's one of those things, right? Yeah. But that's a great question, Skylar. So putting brackets there is just a safer bet, and we're not misstating anything. So we've got a few tests now that we've mastered. The nth term test is what we always do first. If the terms don't go to 0, the series diverges. Then we've got recognizing a geometric series, which is a two-way test. That's the one that looks exponential. And now we have the integral test, which dogs cuss in prison. If you can integrate the rule of sequence, then they have the same behavior. They either both diverge or converge. So that is also a two-way test. Now we have a p-series. Along with the geometric series, the p-series is the second and other recognizable form. And it's another two-way test. So there's two series that you want to recognize, geometric and a p-series. So a series of the form, the integral from 1 to infinity, or 2 to the infinity, or 5 to the infinity, or 0 to infinity. It doesn't really matter where we start, but it's the rule of sequences of the form 1 over n to the p power, or a over n to the p. You can have a constant there that you can pull out. So very similar to the integrals, right? We have the integrals from 1 to infinity. My palm gets in the way. 1 to infinity of 1 over x to the p dx. And we know that these converged as long as it converged to what, by the way? This equaled 1 over p minus 1 if p was greater than 1. So remember, if the power, p for power, on the x in the denominator was bigger than 1, then that essentially made the graph go to the x-axis fast enough to converge. And if we started at 1, not only do we know it converged, we know that it converged to 1 over p minus 1. But if you started at 2 or 3 or 4, it would still converge just to a smaller number. So it's really the same idea here with the series, but we're using n instead of x. So if the power is greater than 1, here's the test. Let's write it down here. If the power equals 1, what can we say if the power equals 1? Then you just get 1 over n to the first. Does that converge or diverge? Diverges. This is called your divergent, but it's so important we list it separately. It's your divergent harmonic series. He's the gatekeeper. For integrals, he's the gatekeeper between do you converge or diverge going towards a vertical or horizontal asymptote. If p is less than 1, it's also going to be divergent. So if you had 1 over n to the 1/2, that's 1 over the square root of n. You can even have 1 over n to the negative 1. What is 1 over n to the negative 1? It's the same as n, right? And that easily would get bigger. So this includes all the negative exponents that end up being in the numerator. But here's the one that we want. If p is greater than 1, then the series converges. Now, unfortunately, for the integral, we could find the sum of the area. But for the p series, if it converges, we cannot find its sum by formula, unfortunately. We can still find an approximation for it, though, like we just did, using the integral test. And so that's not bad. That's not bad. All right, here we go. Example 13. We're going to do this kind of quickly. Determine if the following converge or diverge. Letter A. What do you think? Yeah, you can combine your n. That's n to the first times n to the 1/2. That's n to the 3/2. So this one is convergent, okay? It's a p series. P is equal to 3/2, which is greater than 1. All right? What about the next one? Divergent. If you simplify the n's, you subtract exponents, you end up with 1 minus 1/2, which is 1/2, which when you put that in the bottom, n to the 1/2 is n to the negative 1/2. Yeah, that's how you would simplify it to put it in p series format. So this one diverges. P equals negative 1/2, which is less than or equal to 1. No. You could actually, if you wanted to do it this way, you could say it's 1 to infinity of the square root of n, and now you could say it diverges by what? By the nth term test, right? If you just leave it as the square root of n, then the limit of that goes to infinity, which is not 0. It diverges by the nth term test. If you do bring it to the bottom, which is a little bit counterintuitive, but we did that sometimes with L'Hopital's rule, now it fits a p series, and it also diverges by the p series. So yeah, the tests are going to overlap. There's going to be a lot of overlapping. So good question, Devin. All right, the next one. If you simplify this, you get 1 over the square root of n, which is 1 over n to the 1/2. How about this guy? Does he go fast enough to the x-axis? No. So this one also diverges. It's a p series. P is equal to 1/2, which is less than 1. Would the nth term test work here too for divergence? Would the nth term test work here for divergence? It worked over here because it became the square root of n. And the limit as n goes to infinity of the square root of n is equal to infinity, which is not 0. So the nth term test. This one, though, would be the limit as n goes to infinity of 1 over the square root of n, which equals 0. So the nth term test here is inconclusive. Nth term test is inconclusive. But the p-series test is conclusive. It diverges. All right, how about this guy? Whoa, impressive numerator. Impressive numerator. If you have constants, you can pull them out front. And now it's 1 over n to the 1.1. And you say it's what? It's convergent, right? It's convergent P series. Because P is equal to 1.0001, which is greater than 1. So it converges. Does it converge to 1 over P minus 1? Times 99999? Do we know the summation formula for that? No, not for the series. And you got to be careful. Not for the series. If that were an integral, then we could, if we were finding the area under the curve. But for the P series, we can't find the sum. Not by formula. We can certainly do it by the calculator if we needed to. All right, so everyone okay with P series? We've been kind of, they've been kind of here all along. We started with 1 over n and 1 over n squared. But now we have them legitimately for any power P in the denominator. It only diverges if P is greater than 1. All right, now we're getting into some finer points here. Comparison tests, which we kind of did with integrals. If you have a series that doesn't look exactly like a P series or a geometric series, and the nth term test is inconclusive, and you can't integrate it to use the integral test, you can compare it to something, okay? And it's the same idea as it was with integrals. So here is called the direct comparison test, or what I abbreviate as the DCT. You spell it out on the day of the AP exam. Let's say you have two non-negative series, A sub n and B sub n, or rule of sequences. All right? If B sub n is the bigger one, see that? A sub n is less than or equal to B sub n, so B sub n in this case is the bigger one. If the bigger one converges, what can you say about the smaller one? It also converges. So if the big one is finite, essentially, then anything smaller than finite is still finite. Bless you. And again, if B is the bigger one, but now the smaller one, bless you, the smaller one diverges, what can we say about the bigger one? It also diverges. So these tests don't work. The converse of these tests is not true. Kind of the same thing. If the bigger one diverges, then the smaller one could still diverge, but very possibly could converge. And again, if the smaller one converges, then the bigger one could converge, but it could possibly diverge. So they're only used in one direction. One direction. You think they're ever getting back together? Officially, they're on a hiatus for personal projects. I hope so too. One direction. Yeah, sorry. But they're all doing solo stuff. And I know a couple of their songs because my daughter controls the radio on the ride to school in the morning. Oh man, One Direction, yeah, it was like a hub, and then they all went in opposite or different directions. You can't have 3, 4, 5. How many are there? 7 guys? How many others? 6, 3, 4, 5? 5? How many? 4? You can't have 4 opposite directions. But they took very different directions, right? Niall, he kind of does, he had some, Yeah. Louis, that's the guy I was trying to think of, Little Louis guy. Yeah, his song's kind of weird. But then Harry's kind of trying to be mysterious, isn't he? Yeah, kind of David Bowie-ish. Anyway, we're talking about One Direction. I know you have a favorite. What's that? Vectors? Like for vectors? They'll come back together. By the sum of the vectors, they'll cancel out and they'll be back to where they were in the beginning. Yeah, let's hope so. Let's hope they have a reunion tour. If Zayn is still alive, he smokes. That is. Determine whether the following converge or diverge. Okay, so now I'm not giving you any hint. What's the first thing that we always do, never not first, when we're trying to determine convergence or divergence? Nth term test. Do the terms go to 0? No! Right? The limit as n goes to infinity of 1n cubed over 1n cubed plus 1 is 1, which is not 0. So this thing diverges by the nth term test. I can't even write. You try to write fast and it gets real sloppy. The nth term test. There we go. So you'd be done, right? But let's see. I put it here for a reason. So is there another way to see that it diverges? Well, maybe so. Maybe the nth term test, or maybe the direct comparison test. If I simplified that down, and this is going to be a pretty common thing when you're trying to find the comparison, simplify that down. That simplifies down to, well, yeah, I don't even want to do that. Why would we mess around? Let's not do it. That's going to be a little bit harder to compare directly to something. So let's just keep this. I erased it. I'm thinking about one direction now. I need to stop and purge them from my mind. Okay, I got it. All right, letter B. What does the nth term test say? What's the limit as n goes to infinity of 1 over n cubed plus 1? 0. So now it means, all right, let's get to work. What does your intuition tell you? Convergent. Good. And that's correct. It does converge. Your intuition tells you it converges. This looks so close to a p-series, doesn't it? So close. If that plus 1 were gone, it would be a convergent p-series. So if you had to prove it, because it is so close to a p-series, you would probably want to use the direct comparison. So let's compare to 1 over n cubed, which would be a convergent p-series. And now all we have to do is show, just like with integrals, that if we have something that converges, we have to show that the given one is whatter, bigger or smaller? Yeah. The only way the test works is if we show it's small. If it ends up being bigger, we can't use this test. So here we go. Let's just hope it is. Since 1 over n cubed plus 1 is less than or equal 1 over n cubed for all n greater than or equal to 1, again, we're going to just use the starting value there. Is that true? We stated it. Is it true? It is true, because we're making the denominator bigger, we make it smaller, comma, the integral from n equals 1 to infinity of 1 over n cubed plus 1 converges to. So that's the direct comparison. They'll have the same behavior as long as you can show that inequality for all those n values in the interval. Now, what if that had been 1 over n cubed minus 1? Would your intuition still tell you it would converge? Yes, but would we be able to do the direct comparison test? No. Okay, we would not. So in reality, that plus or minus 1 doesn't really affect it converging, but it does affect the test that we could use to prove it. We would have to use a different test, which would be called the limit comparison test. All right, how about this? 1 over 3 to the n plus 2. What does your intuition tell you? Converge or diverge? Converges, yeah. And the terms go to 0. So it does converge. You're right. It's exponential. This looks a lot like if you got rid of that plus 2, stupid plus 2, let's compare with the integral from n equals 1 to infinity of 1 over 3 to the n, which is actually equal to what? What's another way to write it? 1/3 to the n. Yeah, which is a what? Convergent or divergent? Well, yeah, it's a convergent. We know that. But what type is it? It's a convergent. Yeah, geometric. I wrote p-series. Why do that? I'm glad y'all are here today. Geometric series. So this is kind of what you would have to write if this showed up on a free response. Compare it with this, which is a congruent or convergent, congruent. A convergent geometric series. All right, so since the one we're using to compare it with is a convergent, again, we have to show that the given one was smaller. So let's just go for it. Since 1 over 3 to the n plus 2 is less than or equal 1 over 3 to the n, we don't have to prove that, but is that true? It is, comma, then the series from n equals 1 to infinity of 1 over 3n plus 2 converges as well. Oh, yeah, for all n, thank you, for all n greater than or equal to 1, converges as well. Thank you. So it's almost identical, excuse me, to the integral comparisons that we did. Really the same argument. We're writing a sigma instead of an integral symbol, which means we don't have to put the dx. Every time you write that sigma, and you write the function, do you want to put a dx at the end, or does your mind want to put a dx at the end? Mine does. Yeah. Okay. How about the next one? Intuition. Converge or diverge? Yeah, and you're right. It diverges. Okay? It is so close, it's just a -1. So compare with, now notice we're starting at 4. 4 to infinity of 1 over the square root of n. So for the direct comparison, they're just going to be like one stone throw away. By the way, the nth term test is inconclusive, right? The terms go to 0. So we're going to compare it with that, which is comma, a what? P-series? That one is a divergent P-series. So if it's a divergent one that we are comparing it to, we have to show that the given one is what'er to be conclusive? Bigger. So let's just say since the one we have then is smaller, and it doesn't really matter the order in which you write it down. You could write the one they give you first and then just make it a greater than symbol, as long as the alligator's eating the right one. Yeah? What is an alligator? This is the alligator, right? Comma, and now you just write the whole thing. Oh, yeah, for all n greater than or equal to 4, thank you. Then the given series, which we just rewrite it, diverges also. Same behavior. So, again, you're like, Hope, please don't be on free response. Please don't be on free response. That's a lot of writing. Intuition goes very, very fast. Boom, diverges, done. Okay? So, when you get those multiple choice questions, that's really, really nice. All right, here we go. From 1 to infinity of cosine of n over 2 to the n. Ooh, boy, interesting. Intuition tells you what? Converge. And it does. Okay? The cosine of n, it's just going to oscillate between what? -1 and 1. So we saw this with the integral. We can treat it like a constant pretty much. And now 2 to the n is exponential, or in this case geometric. It's ballooning really fast. It's going to go to 0 very quickly, and the series should converge. So let's compare it with what? What do you think we're going to compare this one to? Very good. 1 over 2 to the n, which is the same as 1/2 to the n, which is a convergent what? Geometric series. A convergent geometric series. And so if the one that we are comparing it to, again, is convergent, we have to show that the other one is what'er? Smaller or equal to, right? It's less than or equal to. So let's go for it and see if it's true. Since cosine of n over 2 to the n is less than or equal to 1 over 2 to the n. We can write that and see if it's true. If it's not true, we got to try a different test. Excellent. Yeah, normally when you put something in the numerator, you're making it bigger, right? Normally, like a 5 or a 7. But cosine of n, like you said, oscillates between -1 and 1. So if you have like a 1/2 in the numerator, it's like making it smaller by a half. You're dividing it by 2. And of course, at the extremes, when it's equal to 1, it's actually equal to the other one. That's why it's less than or equal to. So here we do need the equal sign. And of course, when it's -1, it makes it really small. It makes it negative. So this is true. Very good. This is true. So now we could say, so, or since that, we already said since, comma, the original series from 1 to infinity of cosine of n over 2 to the n, what do we say? Converges to boot. Yeah. 2 words, yeah, to boot. To boot. You getting the hang of it? All right, letter F, intuition. Converge or diverge? Converge. You are correct. It looks so much like 1 over n to the 4th. So let's compare to a summer's day. No, 1 over n to the fourth, which is a convergent, what? P-series. So once again, if it's convergent, we have to show that the given one is what? Smaller. So since 1 over n to the fourth minus 10 is less than or equal 1 over n to the fourth, is that true? Oh yeah, for all n greater than or equal to 2. I don't think so either, actually. That's a minus 10 instead of a plus 10. When it's a minus 10, you're making the denominator smaller, which makes the fraction bigger. Ruh-roh. Ruh-roh. So we can't compare it with 1 over n to the fourth. So guess what? Can't do it with the direct comparison. Your intuition is still spot on. N to the fourth, it doesn't matter if it was n cubed, minus 10n cubed versus plus 10n cubed. It would still converge. Okay, so the minus 10 doesn't have any bearing on that, but it does have a bearing on the test. We can't use the direct comparison. Okay, DCT fails, or maybe we should just say is inconclusive. So what's nice about it is a two-way test. Your comparison tests are always two ways because the one you're comparing it to, you know something about, but it doesn't always work. So man, if there were a way to show that was true, because we so totally know that it does converge. That plus 10 versus minus 10 doesn't have any bearing. Well, there's another test for that called the LCT, which is the limit comparison test. So direct comparison tests work great if there's only like one off from what you're comparing it to, like a plus 1 or a minus 1 in the denominator like we've been doing. Or when it fails, like we just saw, when it's one off. So here's the LCT of the limit comparison test. Again, you have two non-negative sequences. If the limit as n goes to infinity of their quotient, and you can divide them any way you want, okay? Ultimately, one of them is going to be the one that's given to you, and the other one is the one that you're bringing into the comparison. So you can call either one of them A or B. When you divide them and take their limit as n goes to infinity, either way, if that gives you a finite value that is positive, okay? It has to be a finite number, so it can be infinity, and it has to be positive. Then they're going to have the same behavior. Now, most of the time when the direct comparison works, the limit comparison will work as well. So you can kind of do this one most of the time. Now, the reason it works when you flip it either way is because if you do it one way, let's say, and you get a third, that's a finite and positive number. If you actually took the ratio the other way, you would get its reciprocal 3, which is still finite and positive. So it doesn't matter which one you put on top. You just take the limit of the quotient, and if it's a finite positive number, it's going to converge or diverge. So let's come back up here and do this one the other way, using the limit comparison test. So we still think it converges, and it does. So we're still going to compare. We still have to say compare with n equals 2 to infinity of 1 over n to the fourth, comma, a convergent P-series. And now the test is a little bit different. We don't have to show the inequality. We just have to show the limit of their quotient. So we'll say the limit as n goes to infinity. Which one do you want to put in the top? The given or the one we brought? Ours or theirs? Theirs. Okay. That's what I typically do. I put the given one in the top, and I put the one that we have in the bottom. Now, you can actually skip this step if you realize what's going to happen. We have a complex fraction, right? So when you stay, change, flip, you get n to the fourth over n to the fourth minus 10. And, of course, that ratio could be flipped. What's the limit as n goes to infinity? 1. Is 1 positive? Yep. Is it finite? Yes. Okay. So the original series, 1 over n to the fourth minus 10, converges what? What else can we use here? 2 also to boot. How about additionally? That'll work. There you go. We knew it would, right? Now we proved that it did. All right, so let's look over here on example 15. Intuition tells you this infinite series does what? Converge or diverge? Diverge? Converge, yeah. If you look again at the leading terms in the top and bottom, it's kind of growing like a 1 over n squared. Your intuition is right if you say converges. Now, to prove it, I'm not going to use the direct comparison. The direct comparison is just a little bit easier. There's less writing. You just show one inequality. There's really nothing to compute. That's why it has its advantages. But here, the minus 4n and the plus 5, some of those are going to be bigger, some of those are going to be smaller. I don't want to mess around with that. So let's just compare with 1 over n squared, which is, of course, a convergent p-series. So now let's do the test. The limit as n goes to infinity. You know what? You don't have to show the setup. When you do the given divided by 1 over n squared and you do state change flip, what's going to be in the top? N squared over 3n squared minus 4n plus 5. If you want to go straight to that, that's fine. Okay, what did I do? I did this. Just one more time. I'll do it real quickly here without the sigma. I did that divided by 1 over n squared, and then I state change flipped. Okay? And of course, now you look at the limit and you get what? Leading coefficient over leading coefficient, 1/3. So if you choose the series right, if you choose what it boils down to power-wise, you're picking something that ultimately, when you do the division, it ultimately makes the powers the same. So it should be leading coefficient over leading coefficient. So
today there will be a baseball game tonight, and also a dedication to Isaiah Salazar. It's going to be at 6:30, and so guys come out and support. And if you guys please check your emails, teachers, for the morning announcement, and have an awesome weekend.
all right, so to finish this one up over here, since it equals 1/3 and 1/3 is positive and finite, then the given series converges too. Okay? Now, we haven't been doing the nth term test. That's kind of my fault. You should want to get in the habit of doing that first because it'll save you time. It's kind of like evaluating a limit, never not first, direct sub. What happens to the terms here as n goes to infinity? Do they go to 0? You have a 5th degree in the bottom and a 4th degree in the top. 5 goes faster than 4, so the terms do go to 0. Okay, so good. So now it's worthy of our extra efforts. Whenever you have rational functions, which is a polynomial over polynomial, you're going to be using limit comparison test to p-series. And now how do you figure out what you need to compare it to? Just simplify the powers of the leading terms. What's n to the 4th over n to the 5th? N. So you're going to compare it to sigma from 1 to infinity of 1 over n, which is, of course, your what? I'm going to put v, the definite article. It's the divergent harmonic series. It has a specific name. So if you just want to say it's still a divergent p-series, that's fine too. All right, so they're going to have the same behavior if we get a positive finite limit. So now the limit as n goes to infinity of the given n to the 4th plus 10 all over 4n to the 5th minus n cubed plus 7. Now here's the deal. If I divide by 1 over n, it's going to be a lot of writing. So if I state change flip, what's that going to essentially do? It's going to make the n now a factor in the numerator, which you don't even have to simplify. If you were to distribute to every term, that would take a while. You're really only interested in the leading terms, correct? So when you distribute the n to the leading terms, you don't have to show it, but leave it like that. You're going to get 1n to the 5th over 4n to the 5th, which is what? 1/4. So you can kind of save on some of the writing in algebra. Is 1/4 positive and finite? Yeah. So the original series, n to the 4th plus 10 over 4n to the 5th minus n cubed. You can't just say so the series diverges, unfortunately, because we now have two series listed. So you could say that, you can write it out again, and then say it diverges too. Or you can get in the habit of coming up here and labeling that as like J or something, some kind of strange letter. So J diverges too. Okay, but I'll just write out the actual. That's kind of an efficient laziness thing. Typically in your final answer, you don't want to have like saved values. They're good for intermediate calculations, like when we store things as A and B, or we do integral setups. But for final answers, it's kind of nice to have the actual things in there. All right, so you liking the limit comparison test? It's pretty easy. All right, we get to actually use the whole time today. So 1 over n cubed minus 2. If we tried the direct comparison, because it's a minus 2, it's not going to work. So that would be very, very similar to what we just did up here. Do we need to actually do this one? Let's do it very, very informally. What does your intuition tell you about this one? It's convergent. So if we do the limit comparison test, we're going to compare it to 1 over n cubed, which is a convergent p-series. Yes? I'm not going to write out all the notation. So when we do the limit, it's the limit as n goes to infinity of the given one, which is 1 over n cubed minus 2. And if I divide by 1 over n cubed, it's the same as multiplying by its reciprocal, so I get that. And of course, now leading coefficient over leading coefficient is 1. Is 1 positive and finite? Yes. So the series, the given series, converges as well. All right, sweet. This one here, intuition, says what? Diverges. Good. You would compare with what? Yeah, 1 over the square root of n, you said, or n to the 1/2, which is your divergent p-series. And so when you do the limit as n goes to infinity, you're going to have 1 over the square root of 3n minus 2. And when you divide by 1 over the square root of n, it's the same as multiplying by the reciprocal, so you get the square root of n. Now, because they both have square roots, I'll write this extra step, which maybe in the future you don't have to. You can put them both under the radical. And so now they're both to the first power. So you got to be careful. If you are showing your limit work, it has to be the right number. If you ever make a careless mistake, even when you get the right result, you're going to lose points. What is the value of the limit? 1 over the square root of 3, or the square root of 1/3, whatever, which is still positive and finite, right? So they have the same behavior. So the given series diverges. And you don't even have to say as well. You can just say diverges. So why do I bring that up? It has to be the right number. In haste, if you go real fast and you say, oh, it's just leading coefficient over leading coefficient, and you say a third. A third is still positive and finite, yes? So you get the same result. But would you lose points if this were a free response? Yeah, because now you've misspoken, right? You've gotten the wrong value. So just be careful. I know it's sometimes we get carried away. We go fast. We get too excited. At least I do. And that's when you make careless mistakes. So we're done with page 10 of 15. I think we do have time to introduce the alternating series. Okay, this is a very, very important one. The alternating series test, along with the ratio test, probably two of the most important ones. So an alternating series is something that we've seen, right? And it's just kind of a broad category. It's not necessarily geometric, not necessarily p-series. Geometric series could actually be alternating series. So what it means to be an alternating series is you have consecutive terms changing signs. Plus, minus, plus, minus, plus, minus, or minus, plus, minus, plus, minus, plus. So here's an example of an alternating series. You have a positive term, then a negative term, then a positive, then a negative, then a positive, then a negative. The alternators typically show up as negative 1 to the n, negative 1 to the n plus 1, negative 1 to the n minus 1. Those are the typical ones that show up. But there's also another sneaky one that shows up. Sneaky one. And I'm not going to tell you what it is just yet. But what these things do is they only affect the sign of the terms, right? When you plug in a 1, 2, 3, 4, 5, they change signs consecutively for positive n values. They do not contribute to the magnitude. So you have to be careful. If we had a geometric series like negative 1/2 to the n, that's going to be an alternating series, right? But it also affects the magnitude. So you can actually separate the two and say that's negative 1 to the n times 1/2 to the n. It's the same thing, but what you've done now if you separated the alternating piece, okay? This one here is also an alternating series, negative plus, negative plus, negative plus. Now, if you ever see a series that goes like 1 plus 2 minus 3 minus 5 plus 7 plus 6 minus 8 minus 4 plus dot, 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 is that an alternating series? No. The signs do alternate, plus, minus, but they don't do it on consecutive terms. So you might have series that are plus and minus throughout there, but unless they alternate on consecutive terms, it's not going to be an alternating series. Okay, so here's the alternating series test. We probably won't get around to using it, but at least we'll introduce it. If you have a sub n that's greater than 0, so you have a positive sequence, then the alternating series, negative 1 to the n times a sub n, or negative 1 to the n plus 1 a sub n. In other words, if you have an alternator there, you separate the alternator from the rest of the series, okay? So you're isolating the alternator. So like, again, if we had negative 1/2 to the n, if we isolated the alternator, we would let 1/2 to the n be a sub n. So if you isolate the alternator, and it's an alternating series, then if the following two conditions are satisfied, the series will converge. Number one, the limit as n goes to infinity has to be 0. So that's the nth term test, right? In other words, if we apply the nth term test and it passes, if it's an alternating series, if that works, and number two, the series is decreasing or non-increasing. It could actually level out, okay? As long as it's not getting bigger. And again, it doesn't have to be decreasing for all values, just beyond a certain point. This one is typically taken care of when you analyze number one, right? Typically, if things go to 0, they get smaller. But they have worked it in now that sometimes it's not decreasing. So like if you have 1/2, 1/4, right, that gets smaller. And then what if you had like, let's do this. Let me do this. What if you had terms that went like 1/10 and 1/11? And then the next term would be like 1/2 and 1/3. And the next would be 1/12 and 1/13. And the next one would be 1/4 and 1/5. Do these terms go to 0? They actually do go to 0. The terms are going to 0. But are they decreasing? No. The way I'm writing it, I have some small terms, 2 in a row, but then I have some that are a little bit bigger. And then I have some terms that are smaller terms, and then I have some that are a little bit bigger. So this is kind of a weird thing, and we'll talk more about it on Monday, but this one would not qualify. 99.9% of the time, if the limit as n goes to infinity is 0, the terms are going to be decreasing forever beyond the point. If those two things pass, then in the presence of an alternator, the series will converge. So it's almost like the nth term test for convergence, almost, in the presence of an alternator. Okay? We'll stop right there and we'll look at some examples on Monday starting.